Okay, we can start, please.
Yes. So hello, everyone. Today we're going to speak about smart contracts in Ethereum. We will briefly cover Solidity part, but in future lectures, we'll go into like the weeds of Solidity, variables, and etc. Today is like an overall topic, what smart contracts are, and what are like some practices, how to develop them, and how they operate. If you have any questions, just type them in chat. I will reply to them as soon as possible. Yeah, first of all, what is a smart contract? In Ethereum terms, smart contracts are immutable decentralized programs that run deterministically in the context of EVM. They are neither smart nor legal contracts, but the term has stuck. There are several key words in this sentence. For example, immutable. Smart contracts in Ethereum are immutable, meaning that if they are deployed on-chain, the bytecode or the contents of the smart contract cannot be changed. They are decentralized because Ethereum is a decentralized blockchain. Smart contracts also become decentralized once they are deployed. Programs, you can code whatever you want inside a smart contract, and EVM will interpret that and understand. So programs are just like something that EVM or Ethereum as a world computer runs. They are deterministic, meaning that there is no random to somehow alter the state randomly. There are no side effects. So every instruction that smart contract has is totally deterministic and like has only one way of doing stuff. And they are run in the context of EVM. So smart contracts cannot listen to events outside of the EVM. So they are totally contained inside of it. So they are neither smart, nor legal contracts, but it is like the way of saying what they are. Smart contracts are usually written in a high-level language like Solidity or Viper, and then compiled to bytecode. So you can think of smart contracts and the bytecode of smart contracts just like, for example, Java programs. So when you are writing in Java, you're using high-level language to like feed this code to like compiler or the interpreter that will compile or interpret the resulting like low-level code. And this low-level code, as it is for Java, it is the same for EVM, like conceptually. But of course, Java bytecode is much more complex than EVM one. And smart contracts and EVM is Turing complete. So they are really powerful programs. So you can write pretty much arbitrary programs that will do whatever you want, but the resulting bytecode is like limited a lot to make it simple, to make it fast, and to make smart contracts like light to store. Smart contracts are used to bring real-world concepts and value to Ethereum. Yeah, so why would you write a smart contract to like make something valuable on-chain? So there are several concepts that are taken off-chain. For example, ERC20 tokens are just regular cash, or NFTs are just regular collectibles that were brought from real world to Ethereum world. So let's take a look at the life cycle of a smart contract. Number one, smart contract is designed, implemented, and compiled to bytecode. So of course, you would take some time to design and architect the smart contracts you're developing. Then you'll develop the smart contract, and once your Solidity concept, Solidity Smart Contract is finished, you will use the compiler to compile it to a special bytecode and also produce several artifacts like ABI that we will talk about later. So then, once the smart contract is compiled, you will extensively test it and audit. There are tools to test smart contracts manually and automatically that are available for you on your local machine. So you won't need to deploy the smart contract into the mainnet or even testnet. You'll have your own copy or fresh blockchain that is super quick and won't cost you anything to run it and to deploy and test smart contracts there. So there are tools for that. And also the smart contract should be audited because depending on the complexity of the project, you need an external party to take a look at your code and verify that it works as expected. Because usually smart contracts work with value, with money, so you wouldn't be happy if someone lost money due to the bug on your smart contract. Then smart contract is deployed to a testnet or to a mainnet via a special transaction, and its address is determined. So we talked about transaction types in previous lecture or something. So you will use this transaction type to deploy a smart contract. You will set the destination address to 0 and the transaction payload to the smart contract bytecode, the smart contract creation bytecode. And you will also calculate its address, or the node will calculate its address from the deployer address and the nonce of your account. Number 4, users atomically interact with a smart contract either directly or through DAPPs. The contract may in turn interact with other contracts. So what is said here is that you can interact with a smart contract directly, in quotes, using the node itself, or you can use some applications, for example, Uniswap, that has already implemented the manual interaction. So for you as a user, it would just look like that you're clicking a button and everything works seamlessly. Those interactions are atomic because in order to interact with a smart contract, you have to issue a transaction, and transactions are atomic. So it either does what it does or reverse, and nothing happens to the blockchain, to the Ethereum. And smart contracts may in turn interact with other contracts when you're sending a transaction. So when you're sending a transaction, you're setting the data field to call some function. But this function in turn may call other contracts through low-level calls and do what those smart contracts need to do. And if your transaction fails, then all those calls will also fail. So these are not another transactions. They are part of your huge transaction. And number 5, smart contract may be destructed if it allows so. There is a special opcode that EVM has. It's named self-destruct. And smart contracts may implement this opcode if they want. And so when when they call this opcode, the bytecode of the smart contract will be erased, and the amount of Ether that is stored on this smart contract will be sent to the whatever destination you provide. But this is a deprecated feature, so please never use it. Actually, with the future Shanghai upgrade or fork, this will be deprecated on EVM level. So probably compiler will note you that please don't use self-destruct, because in the next future upgrade, when the EOF is introduced, the self-destruct will be removed completely. What are the tools for smart contract testing with manually? Yeah, so I will talk about them in a moment. So here is this moment. Smart contract development environment. So I here give an example of like my favorite environment that I use to develop smart contracts. Its name is Hardhat. It is a TypeScript framework that enables smart contracts developers to build, test, and deploy smart contracts with ease. The framework allows anyone to integrate plugins to add their own functionality to the development flow. And this framework is great for big and complex projects. So basically, it is an NPM package that you can install, for example, to your VS Code project, set it up, and this framework will allow you to following a special project structure to compile contracts by setting the version of the compiler to test those contracts, because this framework comes with the private blockchain, which is a fork of Truffle blockchain, which is a proof of authority, like light Ethereum blockchain, which is like super simplified. And because this framework integrates it into itself, the testing is super easy and seamless. So you will be just typing one command like hardhat test, and it will run the test that you have written. Also, it allows contracts to be deployed to the existing networks and by enabling plugins. So right now, Hardhat doesn't have a specification on how it deploys contracts on its own, but you can download any plugin that you wish from the community plugins and check the manual, how to work with them, and how they deploy smart contracts. So talking about community plugins, there are super many plugins that help developers build smart contracts. For example, the contract sizer that will output the size of the bytecode of the smart contract, the gas estimator that will estimate the gas of every function that is called in the test and output a pretty table saying that, for example, function A took 500,000 gas to execute, and right now it is $25. So considering current network congestion and current Ethereum price. There are, I think, more than 50 plugins available. Some of them we built ourselves. Some of them we use on daily basis. So Hardhat is really amazing, and I recommend using it. One of the most used development environments is Remix, but this Remix is an online IDE for basic smart contract development and interaction. which is great for simple and fast testing, proof of concept writing, and sandboxing. So you probably won't like writing like huge projects with 20 smart contracts or more in Remix, because it is like just inconvenient. It is not that easy to write tests there. It is not that easy to automate deployment. So yeah, if you have one contract or two contracts at most, then using Remix is all right. Also, it is all right to use it for like fast fact checking, for example. Like if you read something in the documentation and want to test it, you will probably launch Remix because it's just super easy and super quick to do. So that is sandboxing that I meant here. Yeah, I also use it pretty much every day to test something, to show like code examples, and yeah, also recommend checking it out. Okay, so we talked about the development of smart contracts and like their kind of deployment, but what is the execution environment of the smart contract? So when you deploy a smart contract to EVM, what does smart contract do to like execute the program that is encoded in its bytecode? So what are, for example, data allocations that the smart contract may use to like execute? So first of all, and the most important one, is stack. EVM is a stack machine, and opcodes, or the like minimal parts of bytecode. So actually, bytecode consists of opcodes, and so these opcodes manipulate stack. So there are like register-based machines and stack-based machines. So EVM is stack-based machine. So it will like set variables or put variables to the top of the stack and manipulate it with opcodes by popping elements from the stack, for example, to add them and pushing the result to the top of the stack. In our case, it will be the addition result. So there are opcodes that, for example, push to stack, draw opcodes that pop from stack, draw opcodes that pop and push to stack. And some opcodes require just one parameter to be like taken from top of the stack, and other opcodes require like 4 or even 5 parameters. Then there is a memory data allocation. So it is the special temporary EVM location where smart contracts store dynamic variables. So this is a location that is fresh to every call, so to every execution context. So if you are calling a smart contract from a smart contract, the memory will like be fresh after the call, but when you return, the old memory like will still be there. So it is allocated every time when there is a call to a new smart contract. And dynamic variables like dynamic arrays or static arrays or structs, like structures. So this data allocation is used to store those variables there. And the reference to this allocation, or the pointer to this location, is stored on stack. So just like in a conventional programming languages. So you can think of this as a heap, and this like as a stack. The third allocation is call data. This is a special allocation that is filled with ABI encoded function call when you're calling a smart contract. It is read-only when you're already called the smart contract, but basically there is an opcode that will copy the required data from memory to call data, and you like can't write directly to this data allocation from the smart contract. But yeah, EVM basically that does it for you. And this can either be, as I've said, the ABI encoded function call, but actually you can pass pretty much anything to the smart contract, but EVM won't just understand this. So then there is a return data. It is the opposite data allocation to the call data. So when you're calling a function, you're filling in the call data, but when you're returning arguments from the function, those arguments will be placed in the return data. So what is important that those two data allocations are used when you're calling another smart contract, but not when you are calling the same functions of the current smart contract. So when you are calling the same functions of the current smart contract, only stack is used. But calling another smart contract, call data and return data are used. Then there is a storage data allocation. It is the smart contract state. So storage is basically your global smart contract variables, so that you are writing in the global scope of the smart contract. And those variables basically like indicate what is the state of current smart contract. And those variables cannot be changed without a transaction. So you can read those variables without sending a transaction, but you can't write to this data allocation without a transaction. Then there is a call stack. So when you're calling many smart contracts in one transaction, the EVM has to understand somehow where to like return. And basically this call stack is used, and it is just the stack of smart contract addresses that like that were called. And also the bytecode data allocation, it is the smart contract logic or the smart contract program that EVM interprets, and this data allocation is immutable. So when the smart contract is deployed, its bytecode is like so EVM understands what bytecode is deployed, and then when the transaction is successful, so bytecode becomes immutable, and you cannot ever change it. Oh yeah, thank you for the question. Is there some limitations on the stack size? Actually, not only the stack size. So talking about the stack, first of all, it cannot expand to more than 1024 elements. If you try to do so, and the transaction will revert. And due to the limitations of the EVM, there are only opcodes to access the topmost 16 elements of the stack. So there are, for example, opcodes that duplicate elements from the stack and put them on top. So you can only duplicate the topmost 16 elements. And if you're trying to reach the element that is deeper than the 16th one, you will also get a revert or even a compilation failure. Memory is also not infinite, even though that you can access up to 2 to the 256 minus 1 memory data locations, which is like super a lot, much more than like x64 operating systems memory. But accessing this memory is not linear. So if you tried, in other words, accessing lower pointers of this memory is cheap, but higher pointers is super expensive. And this function is quadratical. So yeah, at some point of time, you will just run out of gas and run out of Ethereum or Ether to access the memory that is far. Yeah, also there are several limitations to the bytecode. First of all, the execution bytecode of the smart contract cannot exceed 24 kilobytes. And if it does, Ethereum won't accept this smart contract. It will revert on deployment. And with the new Shanghai fork that is in 2 weeks, also the deployment transaction where you're placing the creation bytecode of the smart contract. So this bytecode cannot exceed 68 kilobytes. If it does, your transaction just fails. Okay. So let's just quickly talk about Solidity, what it is. Solidity is a contract-oriented programming language created by Gavin Wood, the former CDO of Ethereum. And its main product is a compiler, SolC, which converts programs to EVM bytecode. The latest SolC version is 0.8.19. Probably we will see 0.8.20 like in several weeks to support the Shanghai fork. So basically, Solidity is the high-level programming language that you use to write programs. And basically, those programs are fed to a SolC compiler that takes them and converts to the EVM bytecode representation. So it also has a lot of amazing functionality like ABI artifacts, and it can also analyze your storage, it can analyze your documentation, and many more. But its main purpose is to efficiently convert your program into the program that EVM understands. Yes, and this language is considered contract-oriented because it is sort of object-oriented, but because there are no objects in Ethereum, there are contracts, so it is like contract-oriented. And okay, let's take a look at the Solidity Smart Contract example. So it is not a complex example. On the left, you can see a high-level Solidity smart contract that you will write. And then on the right, this is the product of the Sol-C compilation. So it converts this text to this like byte string, and this byte string is the bytecode of the smart contract. This is actually a creation bytecode. We will talk about the differences of creation bytecode and execution bytecode in the future lectures. But for now, you just need to understand that this is what EVM understands. And writing programs directly in this opcodes, so it's super, super hard. Okay, so let's just break down this example, what it does. So first of all, we can see the contract being defined. There is an event that we also define. Event is like a special register that usually gets emitted, so the front end or third-party applications may just understand what has happened with the smart contract. There is a storage public variable opener. In Solidity, public variables are not the same public variables as in conventional programming languages. This means that this variable can be read from outside, but still you can't write to this variable directly, only through functions. There is a constructor. The constructor is executed when the smart contract is deployed. And here we set the owner of the smart contract to the message sender. Message sender here is the account that initiated the transaction. It is the deployer of the contract. Then there is a special receive function, which is used to indicate that smart contract is allowed to receive Ether directly. It is not the EVM constraint, it is Solidity constraint. And basically, you have to write this function in Solidity, so the compiler would allow this smart contract to receive Ether. Otherwise, it won't. So this is the signature of this function. And what it does, it just emits this event that we defined above, that smart contract received Ether, and it received message.value Ether. Also, there is a withdraw Ether function, which is defined as external one. And here we have a requirement that only owner is allowed to call this function. Else, we are throwing an error with that not another message. So only owner is allowed to withdraw Ether, no one else. And then we are doing a low-level call to transfer Ether to the owner, because we have already checked that owner is message sender. We are calling the message sender directly, because calling it from owner will just cost a bit more gas. And we are supplying the balance of this smart contract as value, and also the empty data. And then checking that the call is successful, because this low-level call doesn't revert. It returns false if something went wrong. So we have to check that everything is fine. So yeah, this contract can receive Ether directly from anyone. and this receive function is triggered. And then the owner is allowed to withdraw Ether to his own account. Just like that. Where do we take the field message from? Yeah, this field is a globally available like variable that there is an like opcode for taking the value of current call, current transaction, you might say. Also, there is an opcode for taking the sender of current transaction or call, but Solidity is like kind enough to pack those two values into the globally available like variable message. But actually, that's just an opcode that is used underneath. Receive external payable, who can call this in for what purpose? So there is no purpose in this example. It's just an example. But for example, you can write a smart contract that would benefit somehow from this logic. Usually, if you're familiar with proxy smart contracts, they will use the fallback function and do something interesting inside. But here is just an example, and there is no purpose of calling this function, of course, because you will just give someone Ether. Okay. So here is an important question. But how do decentralized applications interact with smart contracts? So I have mentioned several times that in order to interact with a smart contract, you have to initiate a transaction and provide some special bytes, some special encoding as the data of this transaction. So the EVM will be able to interpret this data and call the function that you need. But how the encoding works in like simple terms. So the Sol-C compiler is producing not only the bytecode, but also the ABI representation of the smart contract. ABI stands for Application Binary Interface. So here we have an ABI representation of the smart contract from the example. And what is here? So we have a constructor here, which has no inputs and with state immutability to non-payable. So this state mutability basically means that this constructor is not allowed to receive Ether on deployment. Then we have an event representation, which is not anonymous. It accepts uint 256 variable of type uint 256 with name amount. And yeah, so there are internal types, there are types, so they may differ. But basically it is the representation of your function so that you can just use this information to encode the values that you want to supply to the smart contract so that the smart contract is able to interpret them. And this is called ABI encoding. And this file is used to encode those values. Yeah, then the function owner. So why do we have a function owner here? Because the owner variable is public here. So public variables automatically receive getter functions. So Solidity does it automatically. So we have this getter function here. It returns address, state mutability view, meaning that this function doesn't modify the state of the smart contract, and has a type function. Here we had type event, and here we had type constructor. The visceral other function, which accepts nothing and outputs nothing, it is non-payable, meaning that you can't send other with this function call, also type function, and then the special receive function of type receive, which is payable. So you're allowed to call this function together with other. Okay, and let's just briefly cover what ERC20 and NFTs actually are. So first of all, these are the most used token types. And what they actually are is like a smart contract that is implemented in a way that follows the specification in the special documents, so EAP20 and EAP71. And this smart contract just has an interface. So it has these functions which do what is described in those papers, so that you are like confident that those smart contracts are ERC20 and ERC71 like compliant. Yeah, so they are just regular programs that anyone can write, anyone can deploy, and anyone can use. And the examples of ERC20 tokens are USDT, USDC, DAI, and many, many more. And for NFTs, examples are Bored Ape Yacht Club, CryptoKitties, and etc., etc. So there is no CryptoPunks here, because actually CryptoPunks are NFTs, but they don't follow EAP71 specification. They are like ERC20 tokens, but like coded in a special way, so they are non-fungible. You mentioned smart contracts are immutable, then why there is immutable smart contract exists? Okay, yeah, smart contracts are actually immutable, but upgradable smart contracts don't break this rule. They are just, so this pattern is like implemented in a way using special opcode, which is special opcode, which is delegate call, which saves the state of the contract in a caller contract, but uses the bytecode of the callee contract. So when you're upgrading a contract, you're not modifying the existing bytecode, you're just using another bytecode to alter the state of the caller contract. So there is no like problem here, nothing is broken. It's just a fancy pattern that is used like everywhere. Can a block have both type of transactions? Yeah, so actually these are not transactions, these are contracts, like regular contracts that someone has deployed, and you can interact with them like how you want, when you want. And what EVM will do is call a function of those contracts, so they will update their state And from the EVM point of view, this is just like some call to the some contract that updates something, and EVM doesn't care about what it does. But for you as a user, you have a bias that USDT, for example, has a value of $1, and the wallet will read the state of this known, of this widely known smart contract, and understand how many tokens you have. But what it actually does is that it calls a function like balance of function, which in turn reads some state, reads a variable from the state, which like says that you have 1,000 tokens, and this is it. So yeah, you can have like transactions, whatever you like in a block. Why are CryptoPunks made this way? Because they are so old that they were deployed before the EAP 721 was proposed. So there was no standard. Yes, and CryptoKitties are the ones who proposed the standard and actually implemented the first ones. Yeah, and a really sensitive topic for Solidity developers. So why smart contracts are so attractive for hackers? So first of all, smart contracts work with value. If you are a Solidity developer, that means that you have to be super attentive, because smart contracts will work with something valuable, like tokens are just money. NFTs are just collectibles that's worth money. And usually what smart contracts do is they either produce, transfer, or consume some value. And having bugs in those contracts would result into the loss of value or some gain of value. And yeah, that's why just hackers love those bugs. Then every EVM peculiarity is really hard to embrace. Yes, EVM is complex and fully hard to know every feature and understand its every like move. Why is EVM made this way? And you just learn the hard way, like literally. And usually hackers are focused on one specific attack vector, for example, reentrancy. Yeah, so they will scan your whole application for this one specific attack. But you, as a developer, you have to protect against like 20 attack vectors, and missing one is really easy. But attackers are like experts in one particular attack. So defending from those kind of attacks is really hard. So that is why you need to test your application extensively. That is why you have to have an appropriate development flow, like continuous integration, automatic tests, peer reviews, and of course, an audit. To like it might not be an expensive external audit, but at least it has to be someone that is not involved into the project to take a look at your code, because yeah, you might just miss something, because we are all humans. And innovation is a trial and error. So Solidity, smart contracts, Ethereum is a new technology. And usually when you're building something new, you're doing it wrong. and pure learning is hard way. So building something new might bring a lot of errors, and it is just the way it is. And also, simple human errors might cause a lot of problems. In Ethereum world, it is very obvious because like the market is really rapid, it evolves really fast, so clients want applications to be delivered quickly. This like deadline shrinks, the pressure rises, so humans may just under pressure perform badly. So those errors cause a lot of problems. You might just miss a simple requirement to check, but due to the miss, the attacker might just drain your smart contract, and that's it. And the example of such human error is Ethereum Classic. Yeah. So with Ethereum Classic, there was a problem with some DAO where either the funds actually there was a problem with DAO where the guy destructed the contract and the funds were stuck forever there. And these were millions of dollars back then. So what they did is that they just like forked the chain before this transaction, like nothing happened. And Ethereum Classic was born. Okay, so if you have any questions, please ask. This is it for today.
Okay. Thank you for a lot, Artem. Thank you for a lot for all. And please wait for the update of materials in the classroom. Yeah, and maybe see you soon at the next week.
Yeah, thank you all.
Thank you. Bye-bye.